Lesson: Challenges and limitations of deep learning. Deep learning has revolutionized various fields, including cybersecurity, by providing powerful tools to detect and mitigate cyber threats. However, despite its potential, deep learning also presents numerous challenges and limitations that must be understood and addressed to enhance its effectiveness in cyber defense. One of the significant challenges is the requirement for vast amounts of labeled data to train deep learning models adequately. High-quality, annotated datasets are essential for supervised learning techniques, which dominate deep learning applications. In cybersecurity, obtaining such datasets can be particularly challenging due to the sensitive nature of the data, privacy concerns, and the evolving nature of cyber threats. Furthermore, the manual labeling of data is time-consuming and labor-intensive, which can delay the development and deployment of deep learning models. Another critical limitation is the computational complexity associated with deep learning models. Training deep neural networks requires substantial computational resources, including high-performance GPUs and extensive memory. This requirement can be prohibitive for organizations with limited resources, making it difficult to implement deep learning-based cybersecurity solutions. Additionally, the energy consumption associated with training large-scale deep learning models is significant, raising concerns about the environmental impact and sustainability of these technologies. The interpretability of deep learning models is another significant challenge. Unlike traditional machine learning models, which often provide clear and understandable decision-making processes, deep learning models are often considered black boxes due to their complex architectures and numerous parameters. This lack of transparency can be problematic in cybersecurity, where understanding the reasoning behind a model's decisions is crucial for trust and accountability. For instance, when a deep learning model flags a network activity as malicious, security analysts need to understand the underlying reasons to take appropriate action and improve their defense strategies. Moreover, deep learning models are vulnerable to adversarial attacks, where malicious actors deliberately manipulate input data to deceive the model. These attacks exploit the model's sensitivity to small perturbations, causing it to make incorrect predictions or classifications. In the context of cybersecurity, adversarial attacks can undermine the effectiveness of deep learning-based intrusion detection systems, leading to undetected threats and compromised security. Developing robust models that can withstand adversarial attacks is an ongoing area of research, but it remains a formidable challenge. The issue of overfitting is also prevalent in deep learning. Overfitting occurs when a model performs exceptionally well on training data but fails to generalize to new, unseen data. This problem is exacerbated in cybersecurity due to the dynamic nature of cyber threats, which are constantly evolving and adapting. A model trained on historical data may not effectively detect new types of attacks, leading to reduced performance and increased vulnerability. Techniques such as regularization, dropout, and cross-validation are employed to mitigate overfitting, but achieving the right balance between model complexity and generalization remains challenging. Ethical and privacy concerns also pose significant challenges for deep learning in cybersecurity. The collection and use of vast amounts of data for training models can infringe on individuals' privacy and raise ethical issues. For example, monitoring network traffic or user behavior for threat detection can lead to the inadvertent collection of sensitive information, potentially violating privacy laws and regulations. Ensuring that deep learning applications comply with ethical standards and legal requirements is essential, but it adds another layer of complexity to their deployment and use. Furthermore, the rapid pace of advancements in deep learning technology can lead to a skills gap, where the demand for expertise in developing and implementing these models outstrips the available talent pool. This gap can hinder the adoption of deep learning-based solutions in cybersecurity, as organizations may struggle to find qualified professionals to build, maintain, and interpret these models. Addressing this challenge requires ongoing education and training initiatives to equip the workforce with the necessary skills and knowledge. Finally, The integration of deep learning models into existing cybersecurity infrastructure can be complex and costly. Organizations may need to overhaul their systems and processes to accommodate these advanced technologies, which can be resource intensive and time consuming. Additionally, ensuring interoperability between deep learning models and other security tools is crucial for a cohesive defense strategy, but it can be difficult to achieve in practice. These integration challenges can delay the deployment of deep learning solutions and limit their impact on enhancing cybersecurity. In conclusion, while deep learning holds significant promise for improving cybersecurity, it is not without its challenges and limitations. The need for large labeled datasets, computational complexity, lack of interpretability, vulnerability to adversarial attacks, risk of overfitting, ethical and privacy concerns, skills gap, and integration difficulties all pose significant hurdles. Addressing these challenges requires a multifaceted approach, combining advancements in deep learning research with practical solutions and policies. By understanding and mitigating these limitations, we can harness the full potential of deep learning to enhance cyber defense and protect against evolving threats.